All right, hi everyone, this is Avery again. I'm going to go over project 7, which is about file systems. So this project has actually been given for multiple quarters in CS 110. So as you notice in the starter code and in the spec, it's a lot more polished. And last week, Jerry has also published a bunch of section slides, which were actually, I believe it was when he taught the class, he had these lecture slides. So he basically put all the material that you need to know for this project into those section slides. Before you get started on the project, I highly recommend you read those section slides before you watch the rest of the video. So in this video, instead of going over the concepts, which I know Jerry does super well already, I just want to draw a couple pictures to hopefully get you started thinking about what you're supposed to do for each of these layers that we have to implement. So let's go through them one by one. I might potentially make another video which goes over the starter code. So let's talk about the first layer. The first layer you have to implement is called the block layer. And the purpose of the block layer is to communicate with the disk. Okay, so what does that mean? Well, you can imagine that your file system is represented by a big disk. And this disk is split into sectors. 0, 1, 2, 3, 4, 5, 6, 7. Okay, each of these, this is your disk. And then each of these, we call these sector numbers. Okay, where each of these sectors is 512 bytes. And then the purpose of the block layer is the block layer provides this function called disk image. Let me write the full header. It is int disk image underscore read sector, which takes in a file descriptor, a sector number, and a buffer. Okay, and then the purpose of this function is you can pass in a buffer. Let's say this is a buffer. And then if you give it a sector number, let's say 5, then what disk image read sector will do is it will read the contents of sector 5 into the buffer. Okay, assuming that your buffer has enough space. Okay, yeah, that's the whole point of the block layer. Whenever you need to directly interact with the disk, anytime you need to read some data from the disk into a buffer, you would use disk image underscore read sector. Okay, cool. All right, so now that we have that out of the way, let's move to the next level. So the next level is called the inode level, the inode layer. Okay, and oh, by the way, in the block layer, everything's already implemented for you, so you don't have to implement anything like all. The only thing you have to do is just know when to call disk image read sector in the other levels. In the inode layer, you're going to be implementing metadata for files. Okay, so the other layers might need the metadata for the files that they interact with. So whenever they need to do that, they will call the functions inside this layer. There are two functions you have to implement. One is called inode get underscore get. It takes in a struct Unix file system FS, an int I number, and a struct inode IMP. Okay, so what does that mean? Let me draw that disk out again. So this is your disk. It's split into sectors. I'm going to make the sectors a little smaller. Okay, and then remember how the inodes are laid out. I remember John said in lecture that the inodes can be laid out anywhere in memory, but for this project, the inodes will start at sector 2. So there are each of these inodes is 32 bytes. You can actually count. You can go to the inode.h, which shows you the structure of the inodes, and you can count that each of those take 32 bytes. Each of these sectors are 512 bytes. So if you do the division, you'll see that there's 16 inodes in each. I probably can't draw 16, but I'm just going to try my best. There are a bunch of inodes starting from sector 2. So this first one is inode 0, inode 1, inode 2, and so on. And then starting from sector 3, these would be sectors, inode 16, inode 17, and then you can imagine that from there on, you have more and more inodes until however many inodes you have. Okay, now, so these are all inodes. Okay, yeah, there might be a lot of inodes, so I don't know when this ends. It might keep going on, but starting from sector 2, those are all inodes. The goal of this inode get function is you pass in a file system. I'll go over that. Yeah, you should look at what the file system is. Just go to the Unix file system.h file. You'll see that's basically just, there's a file descriptor in there that will help you call the disk image read sector function. The key point is this I number and this INP. So this last parameter is just an output parameter. It's a pointer to some empty space, and your goal is to populate that space with the inode. I guess the inode is more small. It's like this. It's a small little space that you're going to populate it with the inode. Okay, it's the output parameter. This inode is the interesting part. You are passed in some number, let's say 20, let's say 17. Okay, and the goal of your function is you're supposed to go to the disk and find inode 17. So this inode. Okay, you find inode 17 and then you read it. Your goal is to copy that little piece, that inode, into this area. Okay, yeah, that's really the point of the function. And then the int parameter, I forgot what the int parameter is. That's just 0 if it's success. So 0 success, -1 fail. Okay, so the inode get function basically just finds an inode from the disk and reads it into memory. Okay, it's called inode get. But the issue with that is, remember, you cannot read just a couple bytes from the disk. You have to read a whole sector. Okay, so the point of this function is you have to figure out which sector inode 17 is in, find that sector. So in this case, it would be sector 3. But you would read sector 3 into some buffer, and then you would go through that buffer and pick out which part is I number 17. And you copy that part specifically into the output struct. A couple of tips I have for that, which is when you read this entire thing into a buffer, right? So this is your buffer. Don't declare this buffer as just a character buffer, right? Don't declare it as a char buffer 512. Okay, don't do that, because you know what the type of the objects in that buffer are. It's this buffer is really an array of inode structs. So instead of declaring that, you should just declare this as an array of inode structs. Okay, and there's 16 of them. Yeah, just declare that so that when you actually get the buffer, you can quickly index into them. Here, buffer the first index of that is the inode 17 that you want to copy into the output parameter. Okay, so yeah, don't declare a generic buffer. You know what the type is, just read what that type is. In addition, from CS107, you probably are used to, when you ever need to copy memory, use memset. You should not use memset here. If you, rather than treating this as just a bunch of unrelated collection of bytes, you know that that buffer bracket 1 is a inode struct. So you can copy that directly into IMP. Okay, don't use memset. If you know what the contents are, you can copy, what the sizes are, you can copy that directly. Yeah. So yeah, don't use memset unnecessarily. Don't use generic buffers unnecessarily. Okay, yeah, so that's it for the inode get function. The key part is just you have to do a little math to figure out which sector your inode is in, and within that sector, once you read it to your buffer, which inode is the right one. Now the next function is a little bit more tricky. The next function is called int inode index lookup. It takes in the file system. Not going to write that thing again. It takes a struct inode NP, and it also takes in a block number. Okay, so let's erase this part. Okay, so this INP is simply just this thing. Okay, what the test harness does is it calls inode iget, and then it passes that inode that it just read as the output parameter. It passes it into as an input into inode index lookup. So you get this inode, and your goal is you're given this block number. Now, what is this block number? This block number is saying that within, remember that the inode represents a file, right? So this inode represents a file, and within that inode, there is information about that file. Specifically, the most important information that's stored in the inode is where are the contents of the file, right? That's like a big part of what is stored in the inode, and that is in if you look in the inode struct, there's a little field there called I_adder. That is an array which tells you where the contents of the file are. So for example, let me draw it out. So this inode, let's say this thing looked like this. There's some information about it, about whether it's a directory, there's a mode, I_mode. There's a lot of other stuff in it. So make sure you read the inode.h file to see what it is. But the most important part in there is an I_adder, which stores an array of 8 numbers. That's a little small. Inode. Okay, and these numbers are storing what sectors have the contents of the file. So for example, if the numbers here are 7, 6, and 8, that means that in the disk, let me draw another 6, 7, 8, 9, 10, 11. Then that means that, let me turn these into red. 7, 9, 6, 11. Then that means that the contents of this file that the inode is storing metadata about, the first 512 bytes of that file is stored inside here. So bytes 0 to 511. Then in sector 9, bytes 512 to 1023 are stored there. And then so on. So bytes 1024 to 51535. Okay, and then this could be bytes 1535. It doesn't have to fill up the whole sector. Sometimes it's not completely full, so I might just go up to 1600. Yeah, okay, so the iAdder stores where the contents of the file are. Okay, and then the goal of your inode index lookup function is to determine this block number is saying which block within the file you want, starting from index 0. So suppose I wanted the second block. Well, let's say I wanted the second block. Then how would you find that? You would go to your array and you would see that the second block there is the 6. Okay, so you would know that the contents, this int should be what sector is the inode in? Is the second block in? The answer would be 6. Okay, so that's the goal of the inode index lookup function. Given the block number, like the second block, go into the inode and figure out which sector that second block is in. Okay, if I instead change this to the third block, what would your answer be? Try to come up with the answer. It would be sector 11, right? Because this is the 11 is right over there. Now, this only works for the small, like for small files when you just need direct pointers. When you need more complicated schemes like indirect pointers, then So this is for small files. If instead you had large files, then instead these numbers that are stored here are no longer, these numbers are no longer direct pointers. They don't point directly to the contents of the file. Instead, they point to sectors, and these sectors contain the block numbers. So you might have 7, and then instead of storing the contents of the file, sector 7 actually contains the block numbers. So here, this would be split into a bunch of block numbers, and then within the block numbers, you actually get the let's say sector 9. That means that bytes 0 through 1023, not 1023, 511 are stored here. Okay, so remember, these are called singly indirect numbers, where the numbers that are the sector numbers stored there don't represent the actual file contents. They represent that if you go to that sector, you will find more direct pointers. Okay, and it is only after going to those direct pointers do you get the contents of the file. Okay, so if I have, let's say 11 here, then bytes 512 to 1023 are here. I might have more of these, so these might all be filled up. And then I might have more. Okay, so you might have another one, 8, 6 here, and then these would be more block numbers. One exercise I want you to figure out is, suppose I have, like, let's say the first number here was an 8. Which bytes are written here? Okay, you have to do some math. You might want to review the section slides from, not section slides, the section problem from week 7, where you did a lot of math calculations to figure out which bytes in the file belong to which part in your singly indirect or your doubly indirect. Okay, I'm not going to go into more detail here because you did that last week in section. If you don't remember, go check out that section again. Okay, so this is the inode layer, and these are the 2 functions you have to write. The first function goes into the inode area, and it picks out the inode that you need, given in the inumber, and then the inode index lookup then takes the inode, and it takes the block number, like you want the second block or the third block, and then it outputs which sector you look at. You can imagine, like, in this sequence of events, why that's helpful, right? Let's suppose I know that the file I want is at inode 17, and I know I want the second block. Okay, so if I just know those 2 components, I want inode 17 and I want the second block from it. How can I actually get the contents of the file inode 17 that represented by inode 17 and the second block of it? Well, you can call inode iget to get the actual inode for inode 17. Then you can pass it into inode index lookup. You pass in, you want the second block, and then you get out the sector number 6. What can I do with that sector number? Yes, I can take that sector number, go into the disk, and actually read sector 6 to get the contents of what I wanted. And that's exactly what the file layer does. The file layer, it fetches the contents of the files. Okay, so unlike the inode layer, which just supplies metadata, right? The inode get function gets the inode itself. The inode index lookup looks at the inode and it returns the sector number, but it doesn't actually read the contents. This file layer function, it's called int file get block. The file system, the int inumber, the int block number. So the parameters look suspiciously like the inode index lookup function, with one exception, which is it actually provides the buffer. Okay, so in this function, what you would do is you would, in this function, it's very similar to inode index lookup, but you have to actually read the contents of that sector into buff. Okay, so here, the fundamental question is get the contents of the third block of the file with metadata in inode 26. Okay, so 26 is this inode. You want the third block, another color. 26 is the inode number, 3 is the block number, and then you repeat that process. You using 26, you can actually get the inode to get the actual inode contents. Then using the block number 3, you can go into the inode and pick out the third block number. And using that third block number, you now have a sector number, right? You now know it's in sector 6. You can then go to sector 6 to read the contents into your buffer. Okay. Now, the return value is how many bytes you read. Okay, and let's think about it. When you are reading from like the contents of a file, how many bytes are you reading? Let's say the file has 3 chunks, 3 blocks. Right, this is bytes 0 to 512, bytes this is to 511, 512 to 1023, and then the last one might be from 1024 to, let's say, 1200. Right? If you were reading from block number 0 or block number 1, okay, if you try to reading either of those, then this function should return 512 because you read the whole sector. The whole sector should be put into the buffer. But if you read from the last chunk, if your block number was 2, then it would only return 176 because you did not need the whole sector, right? The file contents only used part of the sector. So when you are trying to figure out what the return value is, you want to figure out whether you are in the last chunk or whether you are not in the last chunk. If you're not in the last chunk, then it's easy. It's just 512. If you are in the last chunk, then you have to actually calculate how much of that last sector are you consuming and return that value. Okay, yeah. Do want to point out that you might be tempted to use disk image read sector also has an int over here. This is always 512 because disk image read sector does not know what the content of the sector is. It's very low level. It doesn't know what the contents are there. The contents there doesn't have any meaning. It just treats the bytes there as stuff to read. So it should always read 512 bytes. You are the one who's responsible for taking those 512 bytes and figuring out what part of it is meaningful. And the number you return here should be like which bytes are actually part of that last chunk in the file. Okay, so that is the file. Yeah, personally, I find this block num to be a very confusing parameter name. So another name you can give it is you can call it a file block number, block index. I feel like this is a slightly better name. It's a little less confusing because this specifically is saying what index in the file. Is it block index 1, block index 0, block index 1, or block index 2? This is a better name because remember previously we technically also called these things. We also called them block numbers. Okay, so yeah, just to not confuse it, let's actually give these a better name. You can also consider renaming these file block index. Okay, yeah, remember these are like the things in red here. Well, not these, I guess. Yeah, these in red, these are block numbers. When we call block numbers, I think of them as sector numbers. They are sector numbers. They are telling you where the contents are in the sectors. Here, they're saying the file contents are actually in the sectors, while these singly indirect numbers are saying the sectors contain the actual block numbers, the direct block numbers. Okay, cool. Now that we've renamed everything, we have everything figured out. Yeah, so let me just draw a diagram. 23, 6. We don't even really need a diagram. This thing just points to a buffer, and then you fill in that buffer by calling the previous functions. You'll need to call both inode get, inode index lookup, and disk image read sector. Okay. Once you're done with this, you should be able to run some tests. So let me actually pull up some tests. In the tests, there are a couple tests you can run. The tests all start like this. You run disk image access -i, and then there's 3 you can run: tests, disks, basic, depth file, and dir f and f name size. Okay, so you should run all 3. All 3 should pass. This -i means only test the first 2 layers, the inode layer and the file layer. You can't test until you've implemented both. So once you're done with the inode layer, try to get it as best as you can, but then work on the file layer. I will mention though that this, I believe, I'm not 100% sure, I believe this first test will pass if you only implement direct pointers. Okay, so if you were a little confused about the singly indirect and the doubly indirect, don't implement all of that at once, just implement the direct pointers. So just implement this first scheme first, just so only the small mode, don't forget about the large file mode. Implement that first and see if you can get basic to pass. Once you're confident that everything except the singly and doubly indirect are working, then you can try these depth files and the dir f name size. I'm not 100% sure, so double check on this. Not 100% sure. Okay, so that's the test. Okay, let's move on to the next layer. So that the next layer is called the directory layer. I use blue, so let's use red. Okay, and then the goal of the directory layer is to or provide information about a single directory entry. Okay, so here's the idea. So the function you have to implement is called int directory find name, and you're given a struct. Let's just do the start fs, the file system, a const char star name. Remember, we're in C now, so no more strings. Int dir I number. So this is an inode number, but you are specifically told that this inode is a directory. And you're also given a dir ent V6 star dir ent. I think you need a struct at the beginning. Anyways, this is the output parameter. Your goal is to populate dir ent. And the question that we're trying to answer is, given that dir I number is an inode for a directory, find the entry, the directory entry for name. Okay, so as an example, the directory entry could be 6, the name could be green.txt, and then this is a pointer to some empty space that you will populate. Let's draw that disk again. 0, 1, 2, 3. Oh, yeah, so you have a bunch of inodes. Inode 6 here. Inode 6 here is the inode that we care about. And in this inode, we're told that this is a directory. Okay, there's a bit in there that represents if it's a directory. Check out inode.h. And you're also told that this is you also have the iadders. It's that array that has all the block numbers. And you might be told that, let's say the block number is 4. Let's make the file system a little smaller so we can draw in the diagram. So let's say it's 4. So if it's 4, then you know that this sector contains the contents of the directory. So here is the contents of the directory. Okay, and then what is the contents of a directory? You should check out the dir ent v6.h file. Dir ent v6.file. You can see what the struct dirent entry v6 is defined as, and you'll know that it has 2 parts to it. One is the inode, and one is the name. Okay, and then what is stored in these tables is it tells you the name. Let's say there's a oolong.txt and there's a green.txt, and there's also like a milk.txt. And then in each row, you also have the inode. So the inode could be 12, 5, 8. Okay. And then your goal here is to, given the dir I number, so you're told that it's in directory entry. That's not do 6. Let's say it was in, 6. Okay. So it was in inode 6. So we read inode 6. We got this inode. We know that the contents of the directory is in the first 512 byte chunks is in sector 4. So we go to sector 4, we read it. And then in that sector, we have a bunch of entries. Okay, these directory entries. Each of these rows, each row is an entry. This is not like in project 5 or 6 where this table is a map, where in C there are no maps. Instead, these are just like structs. This is an array of structs. This is an array of direct EV structs. How many are there? I actually don't remember. 16. Each of these is 16 bytes. So 512 divided by 16. There's like 32 entries. All right. Yeah, there's 32 entries in there, and then you can you read the sector in, and then within this table you can then search for green.txt. Right. You can go through this and you can search. Oh, and you find green.txt. When you get green.txt, then the goal of this directory find name function is simply to retrieve this entry and to put that entry into the output parameter. Okay, so this entry I highlighted in purple, you want to copy that into the output parameter. Okay, yeah, just like the other files, your inodes could have, you can still have the singly indirect, doubly indirect if you have a gigantic directory, but you implemented the singly and the doubly indirect once already in the inode layer, right? Do not re-implement that here. Instead, in your directory layer, you can call the functions from the file layer or from the file layer, from the inode layer, and then only as last resort, when you just need to read the contents of a sector, then you can use disk image read. Okay, but whenever possible, don't re-implement the logic of the singly indirect, doubly indirect. Just use the inode index lookup functions. Okay. Other hints I want to give, yeah, just like in the inode layer, if you are copying the contents of a sector into a large buffer, you know what these buffers, what the buffer is going to contain. It's going to contain dir entry v6 structs, right? It's going to be an array of 32 direct entry structs. So don't declare it as a generic char array. Declare it as a struct, an array of structs. Okay, same reason it's easier to index. Here you can just say that array, get the index 1 entry and copy that into dir, this output parameter. Similarly, don't use memset, don't use any of the very low level stuff. You know the types, you can just copy using the equal sign. Okay, last tip to give is these names are C strings, and you're also given a C string here, name, to compare to. How do you compare to C strings? Remember from CS107, you use stir CMP, stir compare. But there's a slight little weird issue here, and that is these names are 14 bytes long, so they're very restricted. For that reason, how these are implemented is that some of these strings, I forgot if it's some or all, but some of these strings are not null terminated. Okay, they might not have a null terminated sign, and you know from stir compare that you need a null terminal. Okay, otherwise it will read into random trash. So instead of using stir compare, and so don't use, instead of using stir compare, you want to use stir n compare. Okay, so n means you can provide an actual size. Okay, this is important because some of these directory names are not null terminated. I think specifically the ones that are 14 bytes long, so it needs to use every single byte. There's no space for the null terminated. Okay, so make sure you use stir n comp, not stir compare. Okay, and then also this just goes back to the CS107 stuff. When you deal with C strings, be efficient, use as many library functions as you can whenever possible. Don't copy things one byte at a time. Use the library given functions. Cool. Yeah, one last thing, you're guaranteed that the directory names are 14 bytes or less. Yeah. If you want to learn more about implementing more complicated file systems, take CS112. File systems is the final project. All right, that's it for the directory layer. Now we're almost done. The directory layer gives us the ability to, given a name, given a token, to look into a directory, search for that token to get the next inode. Okay, so let's say I have a path. Let's say the path is T. Let's say the path was, do I have an example? Trying to find an example. Okay, T ito n green.txt. Okay, so say you had this path, how would you parse this path? Right, how would you get the contents of green? To get the contents of green, you need to find the inode for green. Okay, but you don't know where the inode for green is. So you sort of do this recursive process where you start with the first part. Well, you first start with the fact that you are in the root directory, right? The root directory has an inode. That inode, you can look in the constants file. The root directory has an inode. You take that inode, and if you look at the inode, you have a directory. So the root inode gives you the directory, root directory, right? And then within the root directory, you can find inode for T. Okay, get the inode for T, and then you can go into the T directory. In the T directory, you will find ito n, and then you can find a node for ito n. Then you can find for ito n, and then inside there, you are now in the ito n directory. And then you can, in the ito n directory, find inode for green. Okay, once you have green, you can then copy contents. Or rather, yeah, you don't copy contents yet, just get the inode. So the goal of the final layer, the path name layer, is to look up a file inode, or look up a file or directory. Inode, given a absolute path. Okay, so what we have up here is an absolute path, and your goal is to loop through it to find the final inode. Okay, so you have to repeat this process of finding the inode, looking in a directory to find the next inode. Okay, so you're gonna have to scan each of these tokens. You're gonna have to look and get the inodes, get the contents of the inodes, look into the directories, and repeat the process. So remember, every time you need to get inodes, you should use the inode layer. Anytime you need to get the contents of an inode, you should use the file layer. Anytime you just want to go into a directory to find the next inode, you should use the directory layer. So use at your disposal all the three levels behind you. Whenever possible, use the higher layers. Avoid digging deep down unless you absolutely need to. Yeah, so this is looking up. The function you have to write is called int path name lookup. And it's very simple. You're given the file system and you're given a path name. Okay, so the path name would be something like this. And then you'd repeat this process of find the root inode, find the root directory, look in the root directory to find the next token, and repeat until you get the final inode. That is the return value. That's the return value. And then whoever called path name lookup can then read the contents of the inode. They can use the file layer, right? The file layer to, given the inode, they can then read the contents into a buffer. All right, couple tips. In this, I'd say that this is the most like 107 intensive thing you'll do here. You'll have to do a lot of string parsing, C string parsing, which I personally hate. It's kind of tedious, but that's what you have to do for this part. And you have to, like our solution uses, like my solution uses the function strlen, stir copy, stir step, and directory file name. Okay, you might want to use stir and copy just to be safe. But yeah, you have to do a lot of string parsing, and then you also have to use the directory layer to be able to go into each directory and find the next token. You can I said like this is kind of recursive. When you do a lot of these like absolute file like path name lookups, they're often recursive. You can implement it both either iteratively or recursively. I highly recommend you do iteratively because it's just easier to use. And if you do recursion, it's very easy to accidentally make a bunch of copies of the file path, of the path name. So I really just recommend you use iterative. If you use recursive, it's very easy to make a mistake and it's harder to debug. Okay, all right, once you're done with that, then you should be able to run the final test, which is disk image access -p, and then all those tests I said, the basic, what was the other one? It was dep file and dir frame fname size. Okay, yeah, and then hopefully if you implement everything correctly, everything should pass. All right, last couple tips. In this project, there's a lot of CS107 stuff, right? There's a lot of string parsing. There's a lot of like memory usage. You have to move around. You have to allocate different buffers. You have to copy different data around. So if you are stuck on something, check out the man pages or Google it just to find the information about it. Try to unblock yourself. Only if you're stuck should you then go on Ed and ask for help. When we've talked a lot about these buffers that you pass into the different functions, you should never use heap allocated memory. Okay, all the buffers you can declare locally. So do not use dynamic memory allocation. Okay, yeah, you will be penalized if you use dynamic memory. So don't use dynamic memory. Valgrind has not worked on any of the previous projects, but Valgrind does work on this project. So you can freely run Valgrind and you should get no errors. Finally, this product is very susceptible to copy pasting, like because you often want to use the same logic for one layer and the other layer. Don't do that. Either unify them into helper functions, or even better, if it's two different layers that we're talking about that wants to share code, just have one layer call the other layer. Cool. All right, yeah, that's it for my overview. Last tip I want to go over, oh, I have one more tip. There's a lot of error checking you have to do. A lot of the return values can be -1 if it fails. I personally recommend you do the error checking at the very end. Save the error checking until the very, very end. You still have to do the error checking and it's still important, but if you do the error checking early, it just makes the code really ugly and it's harder to debug. Okay, and for the TA, seeing a bunch of if this is equal to -1, then abort or something, or actually in this project, just return -1. I believe you usually just return -1 because in C there are there's no exception class you can throw. Yeah, but yeah, save that until the very end. Just saves you some headache and you don't have to look at as many lines of code if you just not have the error statements. All right, that's it for my overview. Let me see if there are any last minute tips I want to give. I don't think so. All right, I hope these diagrams were helpful. Good luck with the project. And if I have some time, I might make another video that goes over the starter code. All right, have a good night. Bye.